Hello, this will be a demonstration of Proposition 9 from Book 3 of Euclid's Elements, which states that if a point be taken within a circle and more than two equal straight lines fall from it to the circle, the point taken is the center of the circle. All we are given is the circle ABC, BC, and some point within the circle. We'll call this D, such that DA is equal to DB, which is equal to DC. And if this be so, then the point D is the center of the circle ABC. We begin by connecting these straight lines AB and BC. That's not connected at all. Like that. We can do that by postulate 1. Next, we bisect AB at point E and BC at point F. We can do that by proposition 110. Next, we join the straight line ED, and then we extend it to the edges of the circle, such that that will be G, and we extend it down like this to K. And similarly, we join the straight line FD by postulate 1, and we extend FD to H and L. We can extend these finite straight lines continuously in a straight line by postulate 2. Now we know that AE and EB must be equal because we made them that way. That is what it means for the point E to bisect the straight line AB. We also know that DA and DB are equal, for that has been given. And we have the straight line ED, which is common. And so we have the two triangles AED and BED, which have 3 sides equal to 3 sides. And so by proposition 1/8, the two triangles are equal in all respects. Namely, that the angle AED is equal to the angle BED. And because these angles are adjacent, each must be a right angle. Therefore, we see that the straight line GK bisects AB at right angles, and because this is so, by the porism of proposition 3:1, we can say that the center of the circle ABC must be on the cutting straight line GK. Similarly, we can show that the center of the circle must also be on the straight line HL. We can do this by having BF equal to FC, and then BD is equal to CD by the given. We have the straight line FD, which is common. And so we have the two triangles BDF and CDF with 3 sides equal to 3 sides, and so they must be equal in all respects, namely that the angle BFD be equal to the angle CFD, and because these angles are adjacent, they must also be right angles. And so HL bisects BC at right angles, and so the center must therefore be on HL. And if the center must simultaneously be on GK and HL, then it must be the point where these two straight lines meet. For if it's not the point where GK and HL meet, then it fails to be on either GK or HL, or it fails to be on both altogether. And we see that the point at which GK and HL intersect is the point D. And so this point D must therefore be the center of the circle ABC. This being what was set out to have been proven, we are done with the proposition, therefore, etc., QED. Nothing to say about this proposition, so I shall simply move on to 3.10.